All right, so now we're going to take a really interesting topic, lean demystified. This topic is just sorely needed. All you have to do is watch LinkedIn a little while and just look at the confusion about in the industry about what lean is, what lean is not, and who better to explain it than Dr. Mark Spearman, who's the technical director here at the Institute and director of technical solutions for strategic project solutions. So Mark has a really interesting background. It may not be familiar with him. He was an associate professor of industrial engineering and management sciences at Northwest University, professor industrial and systems engineering at Georgia Tech, Department of Head of Industrial Engineering and Systems Engineering at Texas A&M. After that, he formed Factory Physics, a consulting and software company dedicated to helping manufacturing companies improve their operations. And then Factory Physics was acquired by SPS in 2018, and he joined the SPS team. Mark is a co-author with Wallace Hopp of the book Factory Physics. So if you've picked up that book and read it, it's a great reference book. I look at it actually frequently, Mark, and appreciate the wisdom that you've captured in terms of that book. So who better to demystify lean for us and talk about how that compares or builds on operations science? Mark, I'm going to turn it over to you and let you take it away.
Thanks, Gary. So can you see my presentation? Yes.
Yes, we can see it.
Okay, so we'll jump into it if I can get it to advance. There we go. So I'm going to talk about first lean without operations science. And gosh, almost like 15 years ago. So I'll talk about the 777 moving assembly line presented by a guy from Boeing. And that got us very interested. And the reason you have moving assembly lines is when the line is stopped, there's some abnormal condition. So stopping the line is a visual that tells you that something's going on. You need to address it quickly. The only problem with the Boeing moving assembly line is it moved inches per hour, not very fast. And so no one really noticed, but that was okay. They still wanted to implement a moving assembly line because that's what their Japanese lean consultants told them they needed to do. So they did it. And 2006, 2007, they spent $250 million on changes on the plant. They lost revenue due to the plant shutdowns, and they reduced throughput to enforce the longest takt time, because one of the issues was not all planes are the same. So the more complex planes, especially the ones with the fancier seats, are the ones that take longer time. So their takt time was 3 days, one plane every 3 days. And that's what it started out with. And then by 2007, they reduced space by 72%. They reduced cycle time slightly, but then they reduced it further. But they did not change the takt time. And so they didn't really increase the throughput. And the throughput was the real issue, because customers of 777s aren't placing their order, 2 weeks before they need it. They place it years before they need it. And so if the backlog has grown really long, they may not place with Boeing. They may go to someplace maybe in France, for instance. So today, well, more recently, by 2022, 2020, the 787 was no longer built on a moving assembly line, but had a stationary assembly. So the question is, they did get some improvement after they implemented the moving assembly line to decrease takt time, increase throughput, but it had nothing to do with the moving assembly line. It was pre-wiring of harnesses and developing new technology for drilling holes in fuselages. And that really had nothing to do with the moving assembly line. So the point is, copying another company, which is different from you, may not be the best way to implement lean. And of course, what we think the best way to implement lean is to use operations science. So we're going to talk about how lean works, first of all, according to the lean gurus, Muda, Mura, and Muri. So 3 Japanese words that start with M. Muda is any activity that consumes resources but doesn't provide value to the customer. It's also known as waste, right? And there's all kinds of muda. There's to transport any excess movement of the product that isn't required by the customer, inventory, any stocks of goods or raw materials, any excess motion of machines or people or equipment waiting on materials, overproduction, producing before it's needed, overprocessing, doing more than customer expectations, and defects. Now, these are the 7 forms of muda as put forward by Taiichi Ono in his book, The Toyota Production System. Since then, other people have added 8, and I think Boeing had 10, but we're going to use the 7 that Ono created. And here's a picture of, transport, inventory, motion, overproduction. And a lot of this is from the leanup.com. And it's good stuff, right? Mura is unevenness in an operation, irregularity or non-uniformity. Mura is the reason for the existence of the 7 wastes. It drives and leads to the muda. And then muri is overburden, beyond capacity or capability. So it exists when machines or operators are utilized at more than 100% of capacity. All right. And what operation science says is you don't even want to get close to 100%, but we'll get to there in a minute. And then we're going to go through a quick review of operation science. So first, what is an operation? An operation is an act that utilizes resources to transform one or more attributes of an entity into some good or service that satisfies some external demand. So the key thing is it requires resources, there's some kind of transformation, and there's some kind of demand. And so those 3 things become critical in understanding how basic operations work: resources, transformation, and demand. All right, so demand is the desire of some customer, and we put that in quotes, for an entity or set of entities with particular attributes. So the customer could be individuals outside the organization, or it could be the machine downstream. So it can be physical, the entities can be physical entities like in production, or it can be information or services. This operation science works for both manufacturing, for projects, and for services. So it's just as applicable in hotels and hospitals as it is in a manufacturing plant. So demand is always satisfied by some process, and a process is usually one or more resources performing the transformation. Variability is a key big thing, and some other speakers have already talked about it. Any dissimilarity between specific instances of a particular entity, the operation, process, or demand. So you can have variability in demand, you can have variability in the process, you can have variability in the entities. We're going to mostly talk about variability in demand and time variability in the processes. Variability always degrades performance. This was one of the laws of factory physics. It prevents the matching of the processes and demand. So you can think of transformation and demand, or processes and demand never perfectly match up. If the process completes first, you have stock. If the demand occurs first, you have a back order or lost demand. So for a service system, the demand always comes first because you don't know what the service is going to be. You can, an ambulance can't say, well, we've already met that. We've already done that emergency, and we stocked it, and here it is off the shelf. You can't stock a service, so it's always back ordered. And then sometimes, if not in services case, obviously, but for production, if you don't have it in stock, it could be lost demand. So how do we buffer this variability? Anytime we have demand and transformation, or demand in a process, there's going to be some buffer in between the two. And that buffer is either an inventory buffer, the transformation before demand, or a time buffer, the demand before the transformation, or a capacity buffer, where we have more capacity than demand. And you may say, well, why would we want more capacity than demand requires? We'll get to that. So if you increase the inventory buffer, you reduce the time buffer, okay, because there's less backorder time. If you increase the time buffer, you reduce the inventory buffer. You make everything make to order, you don't have to have any finished goods inventory. So in that case, those two buffers, the time buffer and the inventory buffer, are kind of mirrors of each other. And so we're going to call it the time inventory buffer as just a single buffer. The time inventory buffer is related to the variation in net inventory. Net inventory can be positive or negative. If it's positive, it's on-hand inventory. If it's negative, it's back orders. And then we have a capacity buffer. And the capacity buffer is basically the installed capacity minus the average demand. So what we want to do is see how these two interact. And so I'm going to show a little simulation. What we have here is a situation where demand is between 1 and 10 with an average of 5. We put in 9 units of capacity. You can see where the line is up here. And the red squiggles are the actual production, and it's trying to keep the net inventory at 0. So if my net inventory started at 3, and I know my average demand is 5, then I'm just going to produce 2, and that'll take me back to 0. If my net inventory is -3, then I'm going to produce 8, and that should take me back to 0. And so this is what you get. When you have plenty of capacity, then the net inventory is here. Here's the target. Here's the capacity buffer. Here's the inventory buffer. And here's the time buffer. So we just made these buffers, from the baseline to the maximum. And so the question is, what happens when we decrease this inventory buffer? Because if we have 9 installed and the average is 50, that's a 55% utilization. That's a 45% capacity buffer. That's a lot of wasted capacity. 45% of the time people are doing nothing. So here's what happens. Both the inventory buffer and the capacity buffer increase. There's the old inventory buffer. There's the old time buffer. And they both increase when we decrease the capacity buffer. So as we squeeze down from here to here, we see the red squiggles get smaller, but the blue squiggles get bigger, and they get bigger, both positive and negative. Okay. So this time inventory buffer we found is the standard deviation of the lead time demand. Demand is random, lead time is random, lead time demand is random. And then here's the formula for it. It's given in factory physics, and we won't get into that. So there's a visual of what the standard deviation of lead time demand. It's not between the maxes, it's what the standard deviation is. And so you can kind of see what that would be. And what we found is that at most production rates, the capacity buffer times this standard deviation of lead time demand, or the time inventory buffer, is approximately equal to the average variability, both the variability in demand and variability in production. And this is a new result that people haven't seen. So here's an example. So demand's down there at the red line, and we have lots of capacity. And so the net inventory stays pretty small. Utilization is much, much less than 100%. When we squeeze it down, this net inventory goes up. And some of that can be positive, some of it can be negative. And so you can see lots of capacity, not much net inventory, limited capacity, more net inventory. And so whether that net inventory is stock or whether it's waiting for replenishment or waiting for satisfaction of demand depends on where you move the target. Okay. So if we reduce the variability, here are two examples of different allocations of the buffers. The total variability goes down, then the total buffers go down as well. So let's look at the lean ideas considering operation science. Muda. So here's all the forms of Muda. Overproduction is inventory, and stocks are stocks. So really those two are the same. Transportation, motion, overprocessing, and defects use capacity. So you can think of that as an unnecessary capacity buffer. And there we agree totally that this is waste. And so eliminate it if you can. Waiting and inventory. Now, this is interesting because waiting and inventory, you can't reduce waiting without increasing inventory. And so here's a graph of basically showing the target for your net inventory called the base stock. And as you increase this target, your back order days go down, but your inventory days go up. So basically, again, those are the mirror of each other. So it's kind of silly to have waiting and inventory being two different forms of Muda, since the only way to reduce them both is to reduce variability. And so if you can reduce variability, then you can reduce both inventory and back order days or time. And that becomes critical. Mura, unevenness in operation, irregularity, or non-uniformity. So here, Mura is getting very close to variability. And we had a chapter in factory physics called The Corrupting Influence of Variability. And the only problem with the lean description of it is it gives no quantitative way to measure it. And it doesn't show what the relationship is to the other buffers. Murray is overburden, which is beyond capacity or capability. And it's when you're over 100%. But what we show is that you need to be much less than 100%. And Toyota has done this. Their classic Toyota production system, 2 shifts, 10 hours, with 2 hours for makeup. Assembly line is tack times are greater than the slowest station. One-piece flow accounts for variation by increasing the tack time. And so the Toyota production system usually has a utilization of about 70 or below 70%. So operation science design, we design with minimum total buffering cost. So what we want to do is consider the cost of maintaining capacity beyond demand, carrying inventory and stockouts and or back orders. We got to optimize all these costs. So here's an example with 83% utilization. The inventory carrying cost is 1.5 million a year. The back order cost is $500,000. Extra capacity is 4 million. Total cost is about 4 million. Now, people say that 83% is a lot higher than 70%. So Toyota kind of overcompensates on the capacity buffer. But a lot of times this is hard to get by the bean counters, and they want more like 90% or 95% utilization. And if you had 95% utilization, you do get a reduction, and you go from 2 million to $500,000 in the capacity cost, extra capacity costs. But your inventory carrying cost to keep the back orders low goes way up. And so your total cost is a 113% increase over optimal. And so the way you implement this is you first go search for the wasted capacity, redesign the same things that Muda mentions, the redesign transport, motion, and overproduction, and any scrap. Then reoptimize the production system. Reduce WIP to reduce cycle time, quickly discover problems, stop and fix the problems, reduces variability, increases capacity, and then you're going to repeat 2 and 4 until you're lean with minimum buffering cost. The big difference with operation science is that every time you change the production system, like you eliminate some problems, you need to reoptimize the production system. And that you can do with something like the production optimizer in the toolkit for PPI. So the conclusions are there is a science of operation. Variability is variability no matter what its source. And extra capacity mitigates the time buffer. OS Lean recognizes that efficient production is usually less profitable. Lean is the process of reducing WIP to eliminate problems. and lean methods without operation science can be disastrous. And usually things get worse before they get better. So when you start reducing the WIP, the inventory buffer, then a lot of times you reduce the throughput. So are there any questions?
There we go, Mark. Thanks. If you can stop sharing so we can see your face more clearly there. Got a question online here. Said, can an agreed upon takt time within a process be a quantitative measure of MURA?
Say again?
Could an agreed upon takt time within a process be a quantitative measure of MURA?
Not by itself. So if you know the takt time and you know the average process times, you can get the utilization. And the utilization relates to MURA. And so you'd have to know what is the longest process time, or what is the longest effective process time. So the takt time by itself, like, Toyota had takt times of 45 seconds and Boeing had takt times of 3 days. It doesn't necessarily mean Boeing is worse. It just depends on, what is the capability of the line.
What they're doing. Yeah, of course. So, the idea that utilization of capacity should be around 70%, even in that vicinity, even 85%, is so contrary to the way project people like me think. In fact, you use, 95%. A common approach, Mark, is for project people to say, I want 110% utilization, because that pressure will create pressure on people to get more done.
Right.
So if I have a stretch target of 110%, then maybe I'll get, 90% out of them or something like that. So what you're saying is so contrary to that. Maybe you could speak to that real quick.
Yeah, it is totally contrary. And people are always surprised when they find out Toyota is like around 70%.
Yeah.
And the 70% comes from, if you have, Toyota just is, classic Toyota was 2-shift production where you had 10 hours of production, 10 hours of demand you're going to satisfy in 12 hours. And the reason you have the extra 2 hours is anytime there's a problem discovered, you pull the andon cord, which stops the whole production line, and you need to make that up. So after the 12 hours, you're always caught up. So you're always on schedule, but you have that extra 2 hours. And then 10 out of 12, that's 83%. But then when you have a one-piece flow on a moving assembly line, you can't set the takt time equal to the average longest process time, because if you did, then half the time that station would stop the whole line, because if it's set at the average, half of them are bigger than the average, half of them are less than the average. And so the ones that are bigger than the average, you'd have to stop the line. So typically you would set it to the right of that, bell-shaped curve, and it might be 83%. And so you take that 83% and the other 83%, multiply them together, and you get about 70%. And then there's never a balance line. So that would be what you would get with a balance line, but there's always different process times on assembly lines, and that takes a little bit more down. So it's at best it's about 70%.
Yeah, interesting.
So it could be less.
Yeah,
but it's very effective. They have no inventory. They have very, very short process, lead times, but it's a little bit over effective. And what we found is you don't need one-piece flow, you need few-piece flow. Okay. And you can achieve that using something like ConWhip, and you don't blow up when something gets shut down. You don't blow up the line with whip, and yet you can still keep the cycle time short. And there's an article in our journal that talks a lot about some of these details.
Okay. Another good question here. How do you measure the cost of back order when it's in the middle of a production system, not at the end? In construction, delay in completion is straightforward. But what about delay in, say, fabrication steps? Do they only matter if it's on the critical path?
That is a good question. And so it turns out that what you're trying to do is get things done pretty much on time. You don't have to have everything done on time. And And one of the things you find is if you had every one of those stations at 99% on time, you have way too much lead time. Okay, because it's not likely that it's going to, all of the steps are going to be long. So what you want to look at is basically the completion time, and realizing that adding up these process times on the critical path or anything, the variance, the ratio of the standard deviation of that total to the mean of that total goes down as you get more and more steps. It goes down by 1 over the square root of the number of steps. And so you don't have to have that 99%. So you don't really need to measure the, back order time of each station or the back order cost of each station. You're really looking at the total. And it just gets in there, you can always translate your desired percent on time to a back order cost. It implies a back order cost. So that's one way to get at it if you need it.
Okay, we got questions rolling in here. So when is it desirable to tip the balance towards back ordering in terms of production?
In terms of production, whenever you have a really great product that a lot of people want and are willing to wait. In fact, James Womack learned about that when he built a bicycle factory for high-end bicycles. And he got them finished very, very quickly. But people who buy high-end bicycles were used to waiting for months. And so when he finished them very quickly, they thought it were less quality. So it actually backfired.
Well, that's a really interesting example. I could see that. Yeah, it's like
Yeah.
a cheap piece of junk sitting on the shelf. Yeah.
Right.
Another question, please define takt time.
Oh, takt time is basically the time between exits of a production line. So usually it's the time between the time at a bottleneck. So, but it's the time between, part A leaves at 12 o'clock and part B leaves at 12:01, then it's a 1-minute takt time.
Okay.
Part 1, part 2.
All right.
And so on.
Hopefully that answered
And
the question.
But the thing is to remember is takt time is simply the reciprocal of throughput. So in operation science, we usually don't talk about takt time, we talk about throughput. But they're just the reciprocal of each other. Throughput is how many parts per unit time. Takt time is how much time per unit part.
So why do you talk about throughput instead of takt time?
That's just easier because demand is measured in throughput. Demand's not measured in takt time. How many parts per month do you sell?
Yeah.
In fact, I got a big argument with a Boeing engineer once about, saying his takt time was 3 days per, the throughput was 3 days per plane. And said, no, the throughput is a third of a plane per day. But people do tend to hate fractional throughputs, but that's what it is. It's a third of a plane per day. And because the dimensions are units over time.
Sure. Another question here. What would be a good strategy to implement OS in highly variable environments such as traditional construction projects?
Well, start with what you have. I'd say go back and look at that list, eliminate the obvious variability. Obvious sources of waste. Eliminate that, look for places that you're doing stuff you don't need to do. We used to go on what we called a waste safari, where we'd walk through the plant and, find things. And it's easier in a plant that's been around for a long time because things, have been put in place years ago and they aren't placed now. Construction sites, it's not so much the case because it's a new site, right? Yeah. But you still can look at your methods and try to eliminate things that are obviously no longer necessary. So you do that first. And then you look at your production system. So you need a model of the production system. And then you want to optimize that production system. And that's what the production optimizer does. It looks at the capacity, you give it capacity and it'll tell you what the optimum WIP should be, what the optimum inventory should be. And, you know, if you give capacity and a target fill rate, you know, percent on time, then it can do those other things. And then it turns out if the inventory or the requirements are so great that, you know, it doesn't make sense, it may be an indication that you need more capacity. So that's the first thing. The first thing is to see, what is my capacity? And
that's basically what we saw in the very first, the second presentation from Garrett and Neal on the actual application of production management and operation science in a construction environment. I think they did exactly what you just said, the way they approached it, the way they analyzed it, they would optimize it, the way they looked at capacity, the whole picture there. So I think the real answer for me, a project guy, is go back and look at that that second presentation again, because that's it in real life. So
yeah, and I would just say anything that's utilized over 85%, give it real consideration.
Yeah. That's a mind bender for a project guy like me. That's a really good new rule of thumb to think about, is the damage we cause ourselves by these things that we try to drive people to do. So Mark, thank you. Excellent.
Thank you.
Good stuff in there. Excellent presentations.